We're doing the last part of this FRQ, but before we go any further, I just want to go over this equilibrium. We've got a solid, some iron 2 hydroxide. This has got a charge of +2. We get that knowing because we know the hydroxide ion, I hope you remember that, has a charge of -1. We'll be using that a lot in the next few units. And this stuff, iron 2 hydroxide, sort of a blackish material, and it's very interesting. If you see some rocks that have got these black stains on them, which have weathered, in this case, a rock formation in Utah, what's happened is bacteria have reacted with the iron in the rocks to very slowly produce the iron 2 hydroxide. This is sometimes referred to as desert varnish. The desert varnish is, it sort of has a nice look to it, but it takes a long time to form. Somehow the bacteria use the charge of the iron 2, and there's an interesting oxidation reaction occurring. People have used desert varnish as a medium for drawing. This art's probably maybe in the area of 6,000 years, which indicates that they carved this black off. They chipped it off, and over these many years in the desert, it has just not changed at all. It's an enduring pigment. In fact, it's been used in cave art for many thousands of years. The black in here can be some carbon, but their preferred material was this black iron 2 oxide. They also use a manganese oxide. In fact, it's still used today. It's called Mars Black, and it's a tattoo ink. And again, it's enduring. You put this underneath some skin, and that black's gonna be there. It's used as nanoparticles for some chemical reactions too. But let's go back to this reaction. Here's our chemist's view of it, but think of this iron hydroxide. Iron 2 hydroxide is a pigment that's been used by our ancestors and even us today regularly as a blackish powder, but it dissolves just slightly. In fact, because it dissolves to such a small degree, it's going to hang around in things without washing away. In fact, earlier you found out that its KSP is really small, 10 to the -14. I mean, if you were to get a decimal point and then 13 zeros and then a 2, you'd have some degree of how little of these ion concentrations are present, because this is the limit. If you try and dissolve this iron 2 oxide, you're not going to end up having, you're going to have very low concentrations of these two things because they multiply out to make this very, very low value. Well, like I said, think of the desert varnish, think of tattoos, think of ancient art when you think of iron 2, or sometimes called ferrous oxide, or if you like the pigment's name, it's Mars, and I think they call it Mars because Mars is considered the patron god of iron, used for weapons and plows. So here's our problem. 50 ml sample of this iron 2 sulfate. This stuff just washes away. It's very soluble, and you should know that this is still +2 and the sulfate's -2. Its molar solubility, its KSP is going to be pretty large because it dissolves very, very nicely. And we have 50 mLs of it, about let's say a third of a cup, a quarter of a cup, or maybe a large test tube. And we mix it with 50 mLs of this concentration sodium hydroxide. Now this is 3,000 molar. That's pretty dilute. This is unbelievably dilute sodium hydroxide. It's got a pH of 8. I'm not sure I could make a sodium hydroxide solution that dilute. It'd be very difficult to produce without using buffers. That's later on. So you've got an extremely dilute solution of sodium hydroxide and a pretty dilute solution of iron 2 sulfate. Does a precipitate form? Okay, this is an RFQ, so FRQ, I should say. This we have to answer this question. Will a precipitate form? We're going to have to say yes or no. I mean, that has to be part of the answer. Whenever you do an FRQ, you remember always answer directly. So yes or no. And then explain and show your calculations to justify your answer. If you just say yes or no, you're not going to get credit for it. You're going to have to explain why. Now, one of the things you should see is that we're mixing two solutions. Originally, this concentration is 3 times 10 to the negative 3 molar. But you're going to be mixing it in water with this stuff, so it's going to go into 100 mLs. So it's no longer 50 mLs of this concentration, but it's been diluted to 100. Likewise, they both dilute one another. So as a result, this is going to be half that concentration. Notice I have the iron plus 2. The iron plus 2 in our final solution is going to be this concentration, half of that. I didn't bother with a calculator. I just wrote it down. You should write this down when you're using an FRQ. And the same thing here. The sodium hydroxide is going to be dilute. They dilute one another. When you mix solutions, each component of the solution is diluted. You can use the dilution equation, but we don't have to. When it's an equal, you can say everything's cut in half. Now, here's our equilibrium expression. The iron concentration, we know that, times the hydroxide ion concentration squared. And we now know both of these. These are given to us in this problem. This is what was mixed together. Here's a student who made this stuff up. What's going to happen? Well, this is our QSP. This is our experiment. This is what's happening. Q. So what's our result? Well, we'll plug these numbers in and see what happens. I'll get my calculator up and put in, hope you know how to use your calculator effectively. I'm going to say 1.5, don't bother with the 0. Second function times 10 to the negative 3 times, now I'm going to be careful because I've got a squared here, and sometimes things can work a little bit funny with the square, so I'm not going to make any chances of having this wrong, times 2, and then second function e negative 6. Don't forget to square it. Set this up in your calculator, on your sheet, when you answer this on an exam. If you got the math wrong, they might give you the point for the setup and even give you full credit for the problem. That's happened on occasion. But let me square this, and let's see what our Q is, the result of this. Let's find this value. Oh, wow, that's small. Decimal point, 14 zeros, and then a 6. This is 6 times 10 to the negative 15. A really, really low number. In fact, actually, this is lower than the KSP. Now, this KSP is the limit. It says if these concentrations are higher to produce a larger value than this, you're going to get a precipitate. That makes sense. This is the solubility limit. You exceed the solubility limit, and you get a speeding ticket. You get a precipitate. Well, we didn't exceed the speed limit. We kept this at less than this. So we've explained or justified our answer with the calculation. My 6 times 10 to the negative 15 is less than that KSP, and with the Q smaller, we're less than the speed limit, no precipitate forms. Now, if you didn't say no precipitate forms, and you just showed the Q smaller than KSP, you wouldn't get the point. Remember, in fact, when I talk to readers, they constantly say, make sure your students answer the questions. Let's go back here. Did we answer the question? Does a precipitate form? No precipitate forms. Oh, no precipitate forms. There's my answer, and I justified it by Q is smaller than KSP. That's my justification. That's not the answer. This is why, and I've shown my calculations. And you don't have to be super neat with your calculations. Just show some numbers so they know that you didn't copy from somebody. So that's our answer for this FRQ. Probably this would be worth 3 points, 3% of a AP exam. And we've got this figured out, and we would know that no precipitate forms, and whenever you see some black stains, desert varnish, some ancient art, or a prehistoric drawing, or even a tattoo, think of iron 2 hydroxide, which has a very limited solubility, which you can always solve for. Congratulations, you now know about KSP and Q.